Okay, this evening we're going to be looking at Module 2, which is mainly going to be creating an assembly called an arbor press. And this is our second project that we're going to be doing in this course. But before we do that, I want to bring back to the front of our minds tolerancing and fits and that process and how to determine them and all that kind of stuff. So we're going to be referencing this handout that we see here. I don't have a PowerPoint presentation. We're really just going to be walking through that handout. I'll be pointing some things out, doing some work along the way. And then we also have this other handout, which is going to be some charts that we're going to reference for practicing determining the fits for some elements. So that's where we're going to start. I am going to actually go underneath my camera here. And here is the start of that handout that I was referring to. So this is a chapter out of a different resource called Tolerances and Fits. So as we look here, what we are going to be doing is focusing on the dimensions that we put on our drawings. We're gonna kind of, dive a little bit deeper into the numbers. As you know, when we create our parts, and you have heard this over and over again, when we put our dimensions on our drawings to identify where our location and sizes of the different features that are there, every one of those dimensions has a tolerance, okay? If there's not a tolerance specifically in back of it, it is going to default to whatever the title block tolerance says, okay? But we also can identify and we can place dimensions on here in limit form or having a bilateral tolerance. So we're going to review all those different ways of doing things so that as we're looking at the projects that we have coming up, we understand and we know that when we have fits that are going to be, especially when they're a little bit more critical to the function of our assembly, we want to be sure that we're specifying the right things. So we're going to be diving deeper into tolerances and specifying them and how to do that. All right. So as we look at the top of page 9.3, methods of specifying tolerances. So we're talking just the English system. So we're going to be just applying the ANSI standards. There's a couple different types of tolerances that we can apply. First and foremost, there is limits, okay? A limit dimension is one where we actually see the high and the low value or the upper and the lower limit of the target that we are going to be trying to achieve, okay? So our tolerance, our total tolerance would be the difference between that high and low value. So in this case, if our low value is 1.370 and our high value is 1.375, the difference between those two is 5 thousandths, okay? When we talk about thousandths is going to be the thousandth place in back of the decimal. So when we're looking in manufacturing, or we're talking in manufacturing, especially if you're in the machining world, you're going to be talking in either thousandths or tenths of thousandths. And that's going to be the decimal place that we see here. So the first place after the decimal is going to be tenths. The next one is going to be hundredths, and then thousandths. And then after that, it's going to be 10 thousandths. Okay. So we in manufacturing kind of live right here at that decimal place. Okay. So when we talk about it's 5 thousandths, it's 0.005. If we say 2 thousandths, it's 0.002. All right. If it's 5 tenths of a thousandths, it's 0.0005. Okay. So when we talk about tolerancing, we a lot of times are referring to that thousandths place. And then here we can see the limit dimensions. Most often we're going to see limit dimensions that are going to be upper and lower to one another. So when we're in our CAD software, whatever it might be, SolidWorks, Creo, AutoCAD, we can play with the settings to achieve this. And we'll see it in application on drawings that we have coming up. The next one that we see here, the type is going to be a bilateral tolerance. This is when we have a tolerance specified in back of the nominal value. So here we have 1.75 plus 3 thousandths minus 2 thousandths. Now, instead of showing what the high and low value is, they're just breaking it out to tell us like how much do we add to that nominal value and how much would we subtract from that nominal value to then come up with our high and low values. In this case, when we have bilateral specified like this, or even with a plus and minus in front of it, it requires the person who is creating it and checking it to do some math in their head, okay, or write it out, okay? It's a little risky, especially when you have things that are more critical. Okay, so for instance, if you have something that is only, maybe a thousandth of an inch difference and it's a small tolerance, by putting something, like this, you're requiring somebody in their head to do that math. Okay, when you put the limits in place, now it's specified. What is the high value? What is the low value? And then you can, figure out more easily by glancing at it. And it doesn't require somebody to make an error with math in their head to determine if you made it to the right size or not. So there are companies that require you to put limit dimensions on for everything. I worked for one, okay, especially when you were in that third and fourth decimal place, something that was critical. So just be aware of that. And then unilateral is where we have a tolerance and you're going to have, if you would, nothing on one side and then all of the tolerance on the other. So in this case, we can see that we have 1.375 plus 0. So that means that the high value here is going to be 1.375 or 1 3/8. And then the low value is going to be subtracting 0.02 off of that. So all of the tolerance, if you would, is on one side, okay, rather than a plus and minus value as we see up here with bilateral. So a number of different ways that we can apply tolerances on our drawings. Now, the last type, which we've, very familiar with, is a general tolerance. So when we don't see tolerance immediately in back of a value on a drawing, like we see here, okay, in these two cases, it defaults to whatever our tolerance in the title block states. So we look at how many decimal places there are, and then we find down here where that is. So for instance, for a 2-place decimal, if there's no tolerance immediately in back of it, we would apply then the 2-place decimal right here, plus or minus 0.01 or 10 thousandths, okay? Now, every company may be slightly different. At WCTC, we use our title block and we apply those to the drawings that we create. So every dimension on a drawing has a tolerance. Also, as we look here, you're going to notice that there are 2 levels of tolerances that default to the title block. Okay, that means that the only dimensions on a drawing that are eligible for no tolerances in back of them are either 2-place or 3-place. Does not apply to 1-place decimals. You would be looking around, somebody would be like saying, oh, you have a 1-place decimal, but I don't see the tolerance title block or the default tolerance in the title block for a 1-place decimal. Okay. You put a 4-place decimal on, there's no default tolerance in the title block. Then that would have to be specified. Okay. So watch each one of your dimensions and make sure that if you are using it and you want it to default to the title block, that it is in a form that has a value there for you. Okay. If not, then you have to put it specifically on there. Okay. It's okay to have a 1-place decimal, but now you've got to add a tolerance to it. Okay. So, so those are kind of things to keep in mind, which I know you've heard before. So some nomenclature or vocabulary, if you would. So first of all, nominal size and basic size, a lot of times are referred to interchangeably. And those are going to be the size that you're kind of, hovering around for whatever you're creating. So for instance, if we go back to the values that we have here on the previous page, the nominal or the basic size would be 1.75. Okay, that's we call it, what's your nominal? And then after that, if that's the target, if you would, that you're trying to hit, then you apply your tolerances to that, knowing that there's going to be variation that you have to deal with. Okay, so nominal size, basic size, interchangeable. Basic size, more specifically, is going to be a size that's going to fall nicely on a nice number in the unit system you're working with. So for instance, if we are in the English system, we are looking at numbers that are going to fall nicely on those fractional values. If we're in the metric system, it's going to be on the millimeter, if you would, rather than, things that are going to be off of that. Actual size is going to be the measured size of whatever that part was when we manufactured it. Now the fit, and this is what we're going to be kind of looking at on a more deep level here today. The fit is going to be the general term that signifies the range for which the tightness of 2 parts are going to go together. So I sometimes say if it's something that has clearance in it, how much slop is there? If you put it together and you can kind of feel a little bit of difference there, What is that clearance value there? What does that fit? How close does it fit? If it's something that's going to go together, you know, almost line to line contact, and it just maybe even taps in, now you've got a fit that's really tight, okay, as opposed to loose. So, so you're going to know based on the function of the parts that you're looking at, you're going to be identifying and defining, you know, what is that fit going to be? Allowance is going to be the minimum clearance space or maximum interference that's intended when you have two parts that are mating together. Okay. Tolerance is going to be the total permissible variation on any given size. So when we look at how high can I go and how low can I go, what's the difference between those two numbers? Like the total tolerance, a lot of times that is referred to as. And then two other terms that are important to know here as well, because they're going to be referenced very soon here, are maximum material condition and least material condition. Okay. Now, maximum material condition is when the maximum amount of material is left over after we've created that feature. Least material condition is when it's going to be just the opposite, when we have the least amount. Now, maximum and least material conditions, for those who had GD&T with me, and many of you have, I think almost everybody, not everybody, but almost everybody. Maximum material condition and least material condition for an external feature of size. Okay, remember that? Remember saying that over and over again. Give me an example of an external feature of size. What would it be? Go ahead. A pin, yes, a pin. I heard pin twice. A shaft, something I like to say I can touch the outsides of. Now, an external feature of size does not have to be a circular feature, but I have to touch it in two places to fully define it. So if I look at, for instance, the diameter here of my pen, okay, and I want to determine what's its diameter, I have to touch it on one side and then directly apart on the other. So I have to touch it in two places, if you would, to fully determine what the actual size is. Okay, that's an external feature of size, right? External feature of size. An internal feature of size is going to be one where I take material away to create it. Okay, so this isn't a great example, but an internal feature of size would, for instance, be the distance between the top of this arch and the bottom here. And what is that value in there? I'm taking out this portion on the inside. I'm removing material to create this feature. I like to say I touch the insides of it then. So a hole, a slot. Again, it doesn't have to be cylindrical. It could be a keyway. All right, something where I took material away and I touched the insides of it in two places to fully define it. Now, once we know if I'm an external or an internal feature, then I can assign MMC and LMC. Maximum material condition. Now, in GD&T, you saw this, abbreviation a lot. MMC-SH, that just means of a shaft, which is an external feature of size. Since it's an external feature of size, its largest size will always be the MMC. Those are easy. External features are easy. And then its least material condition is going to be the smallest size. So here on this external feature of size, this shaft or pin, my MMC is going to be my largest size, the 1.124. That's as high as it can get. The LMC then is going to be the other one, 1.121. Now, when I look at MMC size of a hole or an internal feature, remember, I'm taking material away to create that feature. It's just the opposite. So my MMC is going to be the smallest hole size. So you'll notice here on the hole designation, my smallest value is 1.125 or 1 1/8. And then my LMC is going to be the largest hole size, 1.127. Okay. Now you're going to notice something about the dimensioning here. And this is kind of a, it's not part of the standard, but it's good practice. It's good practice. So it's worth, kind of explaining the difference here. Notice over on the internal feature of size, the hole here, my smallest size is listed on top and my largest size is listed on the bottom. Okay. And when I go over to the external feature of size, the shaft, my largest size is on top. So it's just opposite. And my smallest is on the bottom. I want you to just take 30 seconds to think about why that is. Why that is. So I'm going to give you a little bit of time and I want you to think manufacturing process. Manufacturing process. So much that we do here in design, even though we're not making the parts, they have to be makeable. They have to be made. So we're always thinking about that manufacturing process. So I'm going to ask, why do you think the small size on our internal feature of size, our hole in this case, is listed on top and the largest size is listed on the bottom, rather than where I think we normally see the largest on top, the smallest on the bottom? Why on this internal feature of size do you think it's opposite? And there is a good reason.
It's rather make the hole smaller so that you can also take material away.
That's one reason, and that's a really good reason. Yes, yes. So yes, because when you look at a dimension, usually you look at that top number first, right? You kind of target there, right? So yes, that's a great way. That's a really good thing to think about. Yeah. What's another one? Well, numbers wise, yes, so that they match, yeah, ish. So when you look at the fit here, but let's say I just have somebody who's just interested in making that hole. Okay. Think about how the hole is made and what happens as that drill is used over time. Yes.
It's close to
Well, the actual nominal size is 1 1/8, which is a standard drill size. So I can go over to my tool crib and I can get a drill out that is to that size, which is the nominal size. Yes. But more important, what I'm getting at is, why is the small size on the top and the large size on the bottom, which Lex, you had a really good explanation. I think that's actually really good, but not the one I'm thinking of. Chris, do you have any idea?
If you like make a mistake on a smaller size, then you can correct it, but if you make it too big and you're going for the bigger size, then you can't correct that.
And that's really along the lines what Lex said. Yes, that's a good reason, but not the one I'm thinking of. What happens to a drill size as it is? Oh, I'm so sorry. I've got 2 in the chart here. Because you can make a smaller hole bigger and not a bigger. Okay, great. Yep. So you reiterated, Matthew, you're right on line with 2 other responses here in the room. And Emily said, because it's a fractional value. No, not there. But one thing, I'm glad you brought up fractional values, because I always want to make sure that I talk about it when we talk about dimensioning. There is no place for fractional dimensions in today's day and age. You will see drawings that have fractional dimensions, but always convert them. Okay. So that's not our subject. So go ahead, Josh.
Is it because the drill gets less and less accurate over time?
Oh, it's so good. So Josh said, is it because the drill gets less and less accurate over time? You're on the right track about the drill. You're on the right track, but not quite. What was that? It's going to heat up. Yep, it can heat up. And then what happens to the chips and what happens to the size of the hole as a drill gets dull? Did you have it, James? It does increase, right? Kind of against our intuition. When a drill wears, we think that the drill is getting smaller, right? And you would think it would make a smaller hole. That is not the case. It actually, because of the dullness that's created, the chips in there are getting like larger, and they're actually going to be kind of boring that hole out along with it. And the hole gets larger as that drill dulls. So when we create a hole to a nominal size like 1.125 or 1 1/8, as it is used over time, that hole is going to gradually get larger. So you're going to start at the smallest size based on the standard tooling, but then it's going to get a little bit larger over time. So you've got to kind of watch that. So that's the reason. So I love you want to make it smaller, you know, the sizes on top so that you can only make it bigger, but it also happens that way because of the behavior of the drill as it dulls. Does that make sense to everybody? Do you kind of remember that from manufacturing processes? You think as it would dull and you would think it would get smaller, that the hole would get smaller, but it kind of works in the opposite direction. All right, so moving on. Oh, so MMCs and then why those are there. Let's talk about, I'm going to zoom out here a little bit. How do we calculate allowances? How do we calculate allowances? So an allowance is going to be the minimum amount of clearance that we have when we put two parts together. So if we look at, and really kind of using the hole and shaft example here, but really thinking more along the lines of more generically internal, external features. So these don't have to be circular features when we're applying these fits, but it's just kind of like the majority of what we do. So, so here you're going to see, we're going to take the MMC size of the hole and we're going to subtract off the MMC size of the shaft. So when we talk about allowance, we're interested in what is the minimum amount of clearance that we're going to get, okay, in this case. So if we look at these two values up here, I have the MMCs highlighted. We have 1.125 as our hole, and we have 1.124 as our shaft. So the MMC of each, so the smallest hole, the largest shaft. So you'll notice that when we take the smallest hole first, minus the largest shaft, we get 1/1000th of an inch. And this is a positive value, okay? A positive value. When we have a positive allowance, that means that our hole was larger than our shaft, okay? Because that number was bigger. So that means that we have a clearance when the number is positive. We can have an interference occur where the hole is smaller than the shaft. And in that case, so positive is going to be clearance. And negative is going to be interference. Okay. And interference then means just that that hole is a little bit smaller. It may mean that we have to tap it together or press it together. It may mean that we heat it up or cool it down so that we can get that difference, and then we put it together later on. But neither one is better than the other. It just is letting us know whether we're a clearance or an interference. Okay. Maximum clearance is when we're going to take the LMC of the hole. So that's going to be my largest hole minus my smallest shaft. So that's going to be the maximum clearance that I'm going to get. So this gives me a range, minimum clearance and maximum clearance. Okay. Now here, if we take those two numbers, we get again a positive number. So we know that we're in a clearance situation. And in this case, we're going to go from as little as 1/1000th clearance to as much as 6/1000th clearance. Okay. So the next section here is we're going to look at some examples and we're going to calculate some of these ideas. So in example 9.1, we have a shaft and we have a hole that we are expecting to fit together. And what we want to do is we want to identify the nominal size. Okay. They want us to determine what is the nominal size, what is the tolerance on the shaft, the tolerance on the hole, the allowance, which is the minimum clearance, and what is the maximum clearance between those parts. Okay. So what they've done is they show the items that we're looking for here between these two parts. Now, before we kind of go down into the numbers and see how they got them, what I want to do is identify MMC and LMC. Okay, that's something that's going to always come up. So if we're over on, I always like to start with the external feature. So if we're over on the shaft side here, okay, we know that the MMC goes along with the largest size. So if we compare these two, the MMC is on top. So that's going to be my MMC on the top of the dimension there, which means that my LMC is going to be on the bottom. Okay. So to determine the LMC and the MMC of our shaft, or I'm sorry, of our hole, which is our internal feature, we know that it's just opposite, right? So that means that our smallest hole is going to be our MMC and our largest hole is going to be our LMC. So if we look between these two, my smallest hole is the 1 1/4, 1.25, and the largest hole, LMC, is going to be 1.2504. Okay. All right. Now let's go down into what they're looking for here. So the first thing they want to know is what is the nominal size? The nominal size, again, is going to be kind of that basic size that goes along with, you know, a standard number that we see, you know, in the system that we're working in. So if we look here, you'll notice that on the hole, we have 1 1/4. So 1 1/4 is going to be nominal size. Even though we don't see 1 1/4 specified here on the shaft, it is still the nominal size or the basic size for that shaft because they hover around that. Does that make sense to you guys? Okay. The tolerance on the shaft. Now, when we talk about the tolerance on the shaft, the tolerance is going to be the difference between the highest value and the lowest value. What's that number? Okay. So if we look here on our shaft, we're going to take the difference between the high value, the MMC, minus the LMC. So that math is done right here. So the tolerance on our shaft is a total of, tell me how I would say that, 0.0003. How would I say that in terms of thousandths of an inch? James? 3/10 of a thousand. So if I'm right here, that means it's one more tenth over, right? So 3/10 of a thousand. Good. Then we're going to notice our next one is going to be our hole. So we want to find out what is the tolerance on our hole, the difference between the high and the low value. So we're just going to look at these two values right here. So we're going to take the difference between the LMC and the MMC. So you'll notice they take that difference. We get this number right here. How would we say that number? Yes, you could say, okay, I just got to say it in my head. 4/10,000ths is one of the ideas. How else could we say it? 4/10 of a thousandth, or even just stop at 4/10. Somebody you'll know. So a couple different ways we can do that for sure. Okay, awesome. So any questions about total tolerance here? Or what is the tolerance on the hole? What is the tolerance on the shaft? When we talk about large and small tolerance, if I have a large tolerance, that means that I have a large difference between my minimum and my max. I like to think of a target. Okay. Like how big is the target that I have to hit? A large tolerance is a large target relatively. Okay. Small tolerance is when I have a small target that I want to hit, a small difference between the high and the low. What would you consider these two, 3/10 and 4/10 of a thousandth? Is that like a large tolerance or is that a small tolerance? It's a small tolerance, right? It's pretty tight. Okay. I would say you're taking multiple passes to get to these values. You aren't going to just do it in one, pass of whatever you're dealing with, whether it's a drill or even, you're going to probably put a boring tool in there, maybe even ream it. Okay. So yeah, these are small tolerances as we're seeing them here. If we're looking at, for instance, on the previous page, where we're dealing with 1,000th or 6,000ths, these are larger tolerances, but how would you consider those? 1,000, 6,000ths. They're still kind of tight, especially the 1,000ths. Okay. This one starts to get into a moderate tolerance, I think. Like you do this on a Bridgeport, I like to think of it, right? But this guy, you're putting it across, something, maybe more than one something, right? To achieve that. So as you can imagine, and I want you to think in terms of that and kind of know and be able to kind of identify small tolerances, large tolerances, because the smaller the tolerance, what happens to the cost of that part? It goes up, right? And it goes up really quickly, especially when we start having to get into reaming and broaching and grinding to try to achieve these things. And guess who's in control of the amount of tolerance that's on something? Yeah, point back at yourself. You as the designer, you as the engineer on that product, you are responsible for. And I'm going to say it over and over again. It's one of the biggest responsibilities in a company because it drives the cost of that product. You have to be thinking in terms of not, does my drawing look good? You have to be thinking in terms of every single one of those dimensions, how it is going to affect cost, because the more that something costs, the less likely somebody's going to want to buy it unless it's like amazing, right? So you have to make it affordable and doable. Okay. So tolerances on those holes, the differences. Then we've got the calculations for the allowance, the minimum clearance. And as we know, that's going to be the MMC size of the hole minus the MMC size of the shaft. So we're taking the smallest hole minus the largest shaft. I like to say that's our worst case scenario. That's our worst case scenario. That's the worst fit that we're going to get. And so in this case, when we do that, we go up to our numbers, the MMC size of the hole minus the MMC size of the shaft. Notice that we get a difference of 4/10 of a thousandth here. Tolerance. Positive or negative? Positive, right? So what does that mean? Clearance or interference? It means clearance, right? Okay. So when we put these two parts together, we're expecting them to relatively freely go together. This is a pretty small tolerance. So you feel the sides hit each other a little bit, but for the most part, they're going to go together. Okay. And they'll always have clearance. Because then when we look at our maximum clearance here, we're going to notice that then we're up to 11/10 of a thousandths. Okay. All right. So, so that tells us how it's going to fit together. Those clearances are telling us it's going to freely go together and or come apart. Okay. So any questions on that exercise so far? Okay. Then let's go another one, you know, similar thing, I think. Given the sizes that we have here down below, we want to do that same thing. So on the side, I want you to identify the nominal size, the tolerance on the shaft, the tolerance on the hole, the allowance, and the maximum clearance between. So if you need to use the items up here to kind of, you know, go through and determine what those are, we're going to use these values for the hole and for the shaft. So I'm going to give you a couple minutes to kind of write your notes down for these numbers here, and then we'll compare. All right, let's start looking at each one of these items. Even if you haven't gotten completely through it, that's okay. You can just kind of write them down as we go. So as we look at these two values, or these two, this hole and the shaft, what would you say the nominal size of this pair would be? James? 1 1/4, exactly. Perfect. Yep. So nominal size, 1 1/4. All right. The next part is going to be the tolerance on the shaft. Okay, tolerance on the shaft. So we're looking over here. Tell me how you determine the tolerance on the shaft. What did you do? Chris?
Let me take the maximum. Alright, so we should be able to 16,000.
Yes. So you basically found the difference between these two numbers, right? And you got a value of, I just wrote it out. It's 16 thousandths. So diameter of 0.016. Well, it's not really a diameter. It's a difference of, we're going to do that. Diameters are the values. There you go. So 16 thousandths. Any questions on that? Then we're going to do that very same thing, that same procedure, and we're going to find the difference between the high and the low value of our hole. So here, what is that? What is that value? So 1.266 minus 1.25. It's also 16 thousandths. 16 thousandths. Okay. Yeah, looks like it's right. I didn't bother figuring them out. I just wrote them out. Then we're going to look at allowance. Now from above, allowance is going to be the MMC size of the hole, smallest hole, minus the largest shaft. So again, I like to think of it as the worst case scenario, if you would, when we're putting those things together. So we're going to identify the smallest hole right here, minus the largest shaft. And when we do that, our allowance is 1 1/4 minus 1.238. What is our number here? Please say it louder. I have a hard time. 12 thousandths, 0.012. Okay. Now, positive or negative? It's a positive value. So that tells me, am I clearance or interference? Clearance. Yes. Good. Good, good, good. And then lastly, our maximum clearance is going to be taking the LMC size of the hole, the largest hole size, minus the smallest shaft. Okay. So here we're going to take 1.266 minus 1.222. And what number do we get here? 0.044. Positive, negative? Positive, clearance or interference? Clearance. Okay. All right. Any questions on that information? All right. I know it's probably been a little while since we've thought or talked in those terms, so it's worth kind of going over and refreshing ourselves. Okay. Awesome. So now, ready to turn the page. Let's look at fits. Okay. So fits between mating parts. There are a couple, well, I guess there's 5 different levels of fits officially that we can choose from when we are identifying how we want things to work together. So the first fits that we have are going to be clearance fits. Clearance fits are going to be fits where we always have a space between, in this case, the shaft to the hole. So there's always going to be space relative to that. Okay. So when we put these two together, they're going to go together freely or with, very, very minimal resistance. And we're always going to have a clearance situation where we can kind of feel that gap. Interference is the opposite. Interference is where each one of those want to occupy the same space. So when we try to put those together, we aren't going to have any space relative to them. And so many times with an interference fit, depending on how much interference it is, you may be able to tap it in, you might have to press it in, or you might literally have to heat one of the elements up, cool the other one down to get that space, and then put them together and let them come to ambient temperature. So those are called shrink fits, but those are interference fits because there are parts of each one of those elements that want to occupy the same space. Okay, so that's the next kind. Each one of these is not better than the other. There are situations where we want clearance fits, where we want things to run smoothly with one another. And there are situations when we don't want things to move. Okay, we want them to stay put. So, so it just depends on what is the function that you have. Then between those, there are then some others that are in between, or there are others that kind of fill that gap between purely clearance to purely interference. We've got 2 of them here. One is called a transition fit. A transition fit is where you have part of your tolerance values, like your allowance is going to be a clearance, but then your other side of the fit is going to be a little bit of interference. Okay, we start to get into really small tolerances here. Line to line fit, that means that basically you're going to have to push these together or tap them together. There's not going to be a heavy press, but it's going to be like line to line contact. When we have things that we want to locate and we want them to always go back to the same space, that's going to be a transitional or line contact or line fit. Now, how do we work with these fits? The challenge usually is going to always be, number one, determining which one that is. And I think in a little bit, we get a more, okay, on the next page, we get that definition, which is good. So we need to figure out, first of all, where our function is going to be for the parts that we are determining the tolerances for, or the fits for, okay? And again, we can be anywhere from a clearance fit all the way through a heavy press or a shrink fit, where we have interference. Now, when we're specifying those fits, we are going to be working within one of 2 systems. And this applies to all of the fits, the classes of fits. We're either going to be in the basic hole system or in the basic shaft system. The basic hole system is what you're going to be using 98% of the time. Okay. I never used the shaft system when I was out in industry, and I did a lot of fits. I worked in high-speed packaging environment. So we did a lot of conveyor work. We did a lot of shafts and bearings and all that kind of stuff. I also did wheel housings. So that was another interference fit slash press fits. So we always worked within the basic hole system. Okay. The basic shaft system is there, and we'll talk about it briefly at the end, but what we're going to be using and applying is going to be the basic hole system, because that's what you're going to see again, 98% of the time. I'd say 99 practically. So basic hole system, the basic hole system means that your nominal size or your basic size is going to be on the hole. And for the reasons we identified earlier, which are, we can pull a tool, we can pull a drill off of the shelf, and it's going to be to that nominal size. The shaft, on the other hand, we're going to be setting that up on a lathe, and we can just go in a little bit to make it a little bit smaller, and we don't have to have a specific tool to do that. Okay, we just move the actual tool to create it. So the basic hole system will always have your basic size or your nominal size on the hole, and then it's going to be the differences on the shaft. Oopsie, I'm going to go in here like this. So in this example right here, our nominal size is 1 1/8. So you'll notice that 1 1/8 shows up on the hole. Okay, basic hole system. Your nominal size will be on that hole. On the basic shaft system, your nominal size is going to fall on your shaft. Okay, now I'm not going to say it never happens, but this is going to only happen when, for instance, you are maybe purchasing shaft material or rod material where the nominal size is on the actual shaft, but it's going to be on the high side. So whatever you put it in combination with, you can see, you could even line this up line to line contact, and you could still use the basic hole system and get that nominal size on your hole if you wanted or needed it to be. Okay. So that's the difference between the two fundamentally, but as far as practically how we're going to use them, basic hole system is usually where you want to default unless there's a good reason not to. So let's look at the different classes of fits. How many of you have seen classes of fits before? Okay, if you had me for it, you would have seen it. We haven't spent a whole lot of time here, and that's why we're doing this here, and that's why in this class you're going to be doing more applications of. So here our standard fits are going to be RC, which is called a running or sliding clearance fit, an LC, which is a locational clearance fit, an LT, transitional clearance fit, an LN is going to be a locational interference fit. And then we've got FN, which is going to be a force or a shrink fit. Okay. So the two that end up being used most often are on either sides here. So you usually know if you're in a clearance fit situation, or if you're in a force fit or a shrink fit situation. It's the in-between ones where it's kind of like, I'm not exactly sure what I think it should be. So locational clearance is going to be something where you're going to have line-to-line contact, worst case scenario, but then you're going to be clearance on everything else. Okay. So if you would, the tapping together is going to be your allowance. If you have a transitional clearance or interference, what that means is through that tolerance zone, part of it's going to be a little bit of clearance and part of it intentionally is going to be a little bit of interference. These sound a lot like each other, and they're very close. And then locational interference is when you're still going to see you're going to see interference all the way through, but you are putting it in place so that it stays there. A dowel pin you want for location, you want it to stay in the same place, is going to be a locational interference, not heavy press or heavy force, but a locational interference is we want it to stay there and stick there. We don't want that pin to come out. Okay. If you are wondering which one of these three you need to decide between, you're probably going to be okay no matter which one you do, because they are very close. Okay. And you might get advice from somebody, maybe in the industry, maybe somebody, if you're working out in industry and you're wondering like, what should I use? Go to somebody who's maybe a designer for a while and just ask the question. But by reading those descriptions, you'll get a better idea. But again, the most often we are either in one of these houses. We're either a clearance or we're an interference. Okay, so let's look at our running clearance fits. These are RC fits. There are inside just running clearance fits. There are more than that. 1, 2, 3, 4, 5, 6. Oh, there's 9 classes of fit within there. A 1 is going to be a close sliding fit. So this is your most accurate clearance fit. Okay, so it's going to be the, if you would, tightest. Up on the top end here, when we start seeing LC or RC 8s and 9s, these are going to be loose clearance fits. So these are going to be putting them together and you can literally kind of shake them apart and they're going to be, you know, relative, they're going to be loose relative to one another. Okay. So, so then anything in between. This is where, as the designer, when we start looking at specifying these fits, you have to have your final function in mind. And let's say you pick an RC2 and somebody next to you picks an RC3. I don't know that there's a big difference between that. I don't think I can give an answer and say it is absolutely wrong if you pick a 3 over a 2. You should have picked a 2. Because the descriptions are pretty vague. This is where we have mating parts that need to move and turn easily, but not run freely. Oh, okay. And if you look at 3, this is a precise running fit. This is a precision running or work running at slow speeds or light journal press. Okay. So not running freely, light journal press. This class provides the closest running fits. I don't know, they sound pretty darn close to one another. So again, don't try to split hairs and try to figure out what is the perfect, you know, fit here. If you're kind of in one of these 3 for your application and any one of these can go, pick one. Okay. So, so just so that you know, it's not always going to be a definitive right answer for any one of these, but, you know, pick the one that seems to be the best. So in this case, we've got an RC running clearance fit. So you're going to notice the values of the tolerances here. So if we compare the MMC of the hole, 1.250, to the MMC of the shaft, 1.2496, that's 0.4 of a thousandths difference. Still clearance. Okay, that's our worst case scenario. It's only going to get better from there, but that's an RC1. So that's at the top here, right there, the closest sliding fit. And then if we look at an RC9 for those same numbers, 1.250 to 1.242, that's 8 thousandths difference. So from the top of the classes of fit, RC1 to RC9, in this case, you know, you're seeing a large difference. Okay, but all of them are going to be a clearance fit in the end. The other thing that you're going to note here, and it's worth repeating, notice that my RC1 is a more accurate fit. So I'm holding 0.4 of an inch. Over here, when I look at my RC9, now notice the difference is I've got about 6 thousandths on my hole, 6 thousandths on my shaft. Moderate, you know, type of a tolerance. I'm not going to say wide open, but certainly a large difference between these two. And when we start looking at the function of them, okay, and how it's gonna and how they're gonna be made, which one would you say is gonna be more expensive, an RC1 or an RC9? An RC1, right? We're 0.4 of a thousandth here. We're 6 thousandths down here. Big difference. Okay, so so when we start looking top to bottom, yes, there's a right or a wrong answer. But when we're in the middle here or between, you know, 2 of them or 3 of them that are close, you know, that decision, you just do your best. Okay. All right. The next one is going to be locational clearance fits. So again, these are those ones that are in between the definitively clearance to the definitively interference. And these are LCs. There's 1 through 11. And again, this is going to be normally stationary, can be freely assembled and disassembled. So you've got nice snug fits here. All right. So you'll notice here, these are all to 4 decimal places. This is to 6/10 and 6/10. All right. So that's an LC1. An LC11, you're going to notice that this is again 6 thousandths, 6 thousandths. So within there, you know, there's a large range again. And then we can see the application here of the 2. So this one is going to be a line-to-line contact. And this one here is going to be, you know, there's going to always be clearance. So locational clearance. The next one is a transitional clearance. So again, very similar to the previous one, another accurate locations. We're holding, in this case, these are LT callouts. So LT 1 through LT6. So here's the LT1. Notice that here's a difference of 1,000 about. And then here is the difference of 1,000. And then you'll notice that we have the same on the other side. I think this one's about 10. Oh, about 1,000th as well. Yes. On either side. And here again, we're going to have some that are going to be clearance and some that are going to be interference. Okay. So again, very similar between this and the previous type. And then the last one is a locational interference. So this is going to go from line to line contact to interference. Okay. So I'm just going to kind of point down here. So very similar numbers. So here's our line to line contact and then onto the interference side. So this is, if you would, best case scenario, worst case scenario, right? And again, we're talking, tenths of thousands as the interference. And then the last one is going to be our force fit or our shrink fit. So this is going to be FN1 through FN5. So there's 5 classes of fits in this one. So the FN1 is going to be the light press. So this is going to be something where you can either tap them together or press them together. All right. With heavy force. And then as you go down to an FN4, FN5, then you are going to get into the heavy press fits. And in some cases, shrink fits where you actually have to heat up one, cool down the other, put them together, allow them to cool to ambient temperature or room temperature so that they can share that same space, if you would. Now here, when we look at these values, you're going to notice that your hole, MMC size of your hole, is always going to be smaller than the MMC size of the shaft. Okay. Always. There's going to be press all the way through every one of those sizes. So there's portions of the shaft and the hole that are going to want to occupy that same space. So you'll see that here as well. As you move from FN1 to FN5, you are going to see the amount that you're going to press get larger. And that's where, again, in some cases you can't. When you guys take machine elements class, which is going to be in spring for you guys, it's going to be a spring 1 class. You are going to be looking at the stresses that are incurred because of pressing these values together. You're going to get higher stresses when you press larger amounts of material together than you will when you do smaller. So it kind of makes sense, right? And at sometimes, if you press it too hard, or if you have too much press fit and too much stress builds up, you actually go beyond the elastic limit of the material. And now you've actually kind of destroyed that integrity. So, so you have to be careful with press fits. You just can't say, oh, there's an FN4 and I'm going to do that. That should be totally fine. You have to check the stresses on those when we get into press fits to be sure that you're not exceeding the capabilities of the material. Okay. All right. So let's do a little bit of practice on specifying these fits using that basic hole system first. So what we want to do is we want to determine, we kind of want to determine what is the tolerances that we're going to be putting on a hole and a shaft. So here's our assembly of our 2 parts. Again, internal, external. They don't have to be circular features, but we say hole and shaft a lot of times. So what we want to do is we want to determine what is the tolerance that we're going to be putting on our hole. What is the tolerance we're going to be putting on our shaft? Now up here, what they've done for us is they've told us that we have a nominal size of 1 1/4 inches between the 2 of them. And we want to apply an FN4 fit. Okay. So this is going to be a force fit in the 4th class. Okay. So now we want to find an FN4 fit. Now, where do we find these? There are charts that show us all the standard values. So the other handout that I gave you guys is the one that looks like this. These are the charts with our fits on them. Okay. For those who are virtual, this was the other handout that is part of that module 3. So you're going to notice here that for each one of these pages, we have a class of fits. So we have RC fits here. This is 1 through 4. And as we turn the page, then we get all the way RC 5 through 9. Okay. Then you'll notice it goes in order. Then we have our LC fits, our locational fits. applicational fits, then we have our LT fits, our LN fits. This is another LN. And then lastly, we have the FN fits. This is the fit that we're looking at for this example. So for this example, it wants us to apply an FN4 fit to a nominal size of 1 1/4. Okay. So what we do is we need to locate the chart, which is the FN charts. And now what we're going to do is, see, FN, it was here. There's 2 pages of FN. We want to locate the class of fit that we're going to be applying, and that's an FN4. Okay, so the FN4 is going to be in this column right here. Now down the columns are going to be rows, and over on the left-hand side, this is going to be the nominal size range for whatever your nominal is. So we're going to go down here, and we're going to find the row that 1 1/4 would fit on. So you're going to notice that this goes to 1.19, and then from 1.19 to 1.58. So 1 1/4 lands in between those two numbers. So that means that we're going to be working on this row over to the FN4 fits. Okay. So we're going to be right here on this column for our fit. Okay. So now you'll see that in that FN4 column, we have first a row, or I'm sorry, a column that says limits of interference. This is going to be our min and our max interferences that we're going to have. Then underneath here, we're going to have the hole size and the shaft size. Okay. So if we go down, you're going to notice that this is going to give us then on our nominal size, we're going to add 1 and subtract 0 for the hole. And then we're going to add 3.5 and subtract 2.5. Now, those numbers are not 1 inch, 3.1 inches. All the numbers in these charts are in the 1,000th of an inch, okay? In the 1,000th of an inch. So if we look at, for instance, 1, so if I take the number 1.0, that is 1,000th of an inch, which means that if we look at it in terms of, you know, using it for our tolerancing, we're going to move this 1, 2, 3 to the left. So that means that 1 is actually 0.001. It's 1,000th in this chart. Okay. If we look at the 3.1, so if we take 3.1, it's 1, 2, 3 to the left. So that means it's 2 zeros in front of there, 0.0031. Okay. So what we want to do then is we want to apply these tolerances to our nominal value. So if we know that our nominal value is 1.25 inches, right? 1.250. I'll put a third place there. On my whole column here, that means that I'm going to add 0.001 and I'm going to subtract 0. So now my limits of size are going to be adding and subtracting. So my limits of size are going to be 1.250 on my whole. I'm sorry, 1.251 on my whole over 1.250. 1.250. Okay. So those would be the limits of the whole for this application. So if I look back at this example, you're going to notice that 1.250 to 1.251. Now they put the smaller nominal size on top for those reasons we talked about earlier. Now, if I'm going to tell you this, if you don't do that in your work, it's not something that violates the standard. It's okay. But you may see it at times and wonder, why is that there? Or if you're like, no, I want to practice that. That makes sense. I want to show people I know what I'm talking about, because that's kind of I'm going to say it, it's kind of an old thing to do, but it still is a good practice for good reasons. So that's why you see that number on top there. But when you do it in, for instance, Creo, the standard is going to be the higher number is going to be on the top and the lower one's going to be on the bottom. Okay. Now let's do the same thing for our shaft. So we start again with our nominal value of 1.250. This time we're going to add 0.0031 and we're going to subtract 0.0025. So here, what would my values be? It would be 1.2531, 1.2475. Is that right? Okay. Scary that I'm in my head. And these are going to be then the limits of the shaft. Okay. Now these limits are to 4 decimal places. Okay. And these were to 3. So what you'll notice is when you have 2 parts that are going to work together, even though they might not be on the same drawing, you typically do give both of them 4 decimal places. Okay. If one is 4, you do the other 4. One is 3, the other one's going to be 3. Okay. So that would be how you would line those up. Right. So any questions on how to apply a fit for Tanner? Thank you. Say that again. Oh, thank you. No, you're right. You're right. Oh, thank you, Tanner. Thank you. Thank you. Thank you. You all see, don't be afraid to try that. Yes. Talking and writing at the same time. I'm not always as good as I should be. Thank you, Tanner, for pointing that out. Yes, it's a plus 2.5 at the bottom. I did a subtraction just, I think, out of habit. So it's a plus and a plus. So yes, this would be my my value then. Thank you for pointing that out. So these would be the limits then that we would apply on the shaft side. Okay, which would ensure that we would have the FN4 fit. So you don't have to, pick a fit and then all of a sudden have to out of, the air, pick out what your values need to be. You can find out where your nominal value is, pick your fit, and now the chart gives you your pluses and your minuses for the internal and the external feature, okay, that are going to fit together. All right. How many have used this before? Some of you haven't. Okay. All right. If we turn the page, let's do one more. Okay. Want you guys to kind of write this out on your own using the chart. I'll kind of walk through this with you as well, but I want to make sure that we get the same numbers that they have there so that you understand how to look for and apply these values. So in this case, we want to do an RC6 fit, which is a running clearance fit on a nominal size of 3/4 of an inch. Okay, nominal size of 3/4 of an inch. So RC was the first page of this handout, and an RC6 is going to be on the second page. So we're going to go over to the second page, find the RC6, and then down the nominal size column here, we want to find where 3/4 of an inch is going to fall. So it looks like it's going to be the 5th row down. Okay. So now we're going to take our 3/4 of an inch, and this is the limits of clearance. Okay. But we're going to be interested in what is the tolerance we're going to apply to our hole and what we're going to apply to our shaft. So in this case, 3/4 of an inch or 0.75 is our nominal size. So 0.750, and I'm going to do the hole first. Try to do this without a mistake. So this is going to be plus 0.02 minus 0. So my limits here are going to be 0.752 to 0.750, right? And that's for the hole. For the shaft, start with my same number, 0.750. This time we're going to subtract. So we're going to subtract, 0.0016 and subtract 0.0028. Now I'd have to do that math, but I'm pretty sure the numbers are going to come out to be what we see right here, 0.4 or 7.74, 84, 0.7472. And those are going to be the values there. Okay. Now, again, 4 places on both of them because they're mating together so that you can see that there. Any questions on those? Okay. And the key here is in these charts, first of all, at the top, it gives you the description. So if you're interested in, kind of getting a better idea of what each one of those means. And then down here, understanding that these numbers are to the 1,000th of an inch. Okay, 1,000ths of an inch. So you're going to move that decimal place to the left 3 times. Okay. All righty. So now the very last page that we have here is the basic shaft system. Now here again, like I said earlier, this is going to be something that you are probably may never even use, but it's another option out there. And what happens is you put the nominal size on the shaft. So this is the basic hole system for an RC6 fit. And the charts are set up as the basic hole system. Okay, so we have to do kind of a little bit of a conversion, if you would, and I'll show you that in just a bit here. So what you do is you look at your shaft. And remember, this is based on the nominal size on the basic hole system. The shaft right now on that high value is going to be a minus 16/10 of a thousandth, okay, or a 0.0016. Now, since it's there and we want to get the nominal value in here, we're going to take that number no matter what it is, and we're going to add it so that we're going to add 0.01 or 0.0016 to all of the numbers. So if we look down here, what happens is our shaft is going to be a minus 0 now. And that's going to mean that my 0.75 is going to be on the shaft. But I added 0.0016 to that value. I added it to this value on the bottom. So notice that now this went to a negative 0.12. And then over on this side, I added 0.0016 and added 0.0016 here. So it's kind of like you have to convert the table so that you can get the shaft to be the nominal size. All right. So the same range of tolerances applies to both. It's just that the numbers are going to be a little different, and that nominal size now is going to be on the shaft as opposed to on the hole. Okay. So they do an example down here. I'm not going to worry about an example like that. Again, I'm not going to test you on that. I just want you aware of it and how it works and that it is out there. So if you do come upon it, that you kind of know how to deal with it. So what I want to kind of show you now is you have a practice problems that directly relate to what we had just talked about. So I want to go back to module 2. And you'll notice here in module 2, we have some practice problems. Now, this practice problems, this set of practice problems, if you click on it, this is going to be, I'm going to say in quotes, a little quiz. Okay. And the little quiz has to do with, I have different things for you. I think I can go to next. Maybe not. Hold on. I was going to try to show you a view of it, but I think if I go to view as a student and I go down to module 2 and I click on it, I think here now you'll see. So this is going to be a little quiz. It's going to be multiple choice, true, false, but there's also some short answer, or kind of, they call it essay, but it is short answer. So if we begin this, the ones that are short answer, I will have to correct. I think there's 6 of them in there. So there's going to be 6 questions that won't get graded. So the first one here says define tolerance. So then there's a text box here where you can fill in. Now, I don't want 1 or 2 words, and I don't really want you to go in and just copy whatever the definition is. Put it in your own words. Tell me what tolerance means to you, because at this point in the program, you should have some sense. The next one is, why are tolerances important to a technical drawing? Okay, why do we have them on there? What is that? Why are they important? Then you want to define limits. And then there's going to be some multiple choice questions. There's going to be a couple true, false, and then maybe a couple more essays sprinkled in. These are the ones I just wanted to point out to you. Starting with, I think, number 10, I think there's 3 or 4 where using the basic hole system, determine the size limits of the hole and the size limits of the shaft for a nominal size of 1.5 with an RC3 fit. So this one is going to be worth 4 points because there's going to be 2 values on your shaft, 2 values on your hole. Make sure you don't have to show me your work, but let me know hole, min and max, shaft, min and max, so that I can make sure that you applied that RC fit, to the 1.5 inch diameter nominal size. Then you're going to notice there's another one here, 3/4 of an inch to an LC7. And then we've got a 1/2 inch to an FN5. And then you've got a 1 inch to an LN2. Okay, so just kind of making sure we're practicing and understanding how the charts work. And then again, some multiple choice, true, false, and so on. So that is going to be the module 2 practice problems that you have. These are, on the calendar, these are due, I believe, at the end of the week. So, so a little bit different than the practice problems that we've done before. Sorry. I'm gonna return. I think I want to go back over here. There we go. So any questions about tolerances, fits, and then the module 2 practice problems? I don't know. I think so. I'll have to look. I'll have to look. I'm not sure. Great, good question. Lex had, is it one attempt? I don't know. I don't remember if I set that. I'll look in just a little bit. I don't think it's gonna be, maybe, should I be nice and give it unlimited? How about I do that? One attempt, Lex says just one attempt. I only need one attempt. Hunger Games. I think there might be multiples. That's what I don't want to do. Yeah, I know. No, that would be terrible. Okay, so that's that. Any questions on I'll give you more information about the number of attempts. I don't, at the top of my head, I don't know. All right, so then I'm gonna stop the recording here and I'll let you guys, take a peek at that, and then we'll start looking at the other elements, so.